Okay, guys, coming in for pre-calculus, our lesson for today is to actually kind of look more into these sinusoid applications, very similar to the Desmos activity that you did on burning daylight. So we're going to kind of work through a couple of examples of this. This first video is going to focus on a Ferris wheel problem that's moving around in a circle, and this idea of a lot of our applications are that pretty much anything that exhibits a repeating pattern of behavior is exhibiting what we call sinusoidal behavior. So anything that moves around in a circular motion would definitely be included in this class of functions, or anything like we're going to look at in example 2, which will probably be the second video, a spring, something that moves up and down in a fashion like a spring bobbing on the end of a weight bobbing on the end of a spring, are going to be examples of this sinusoidal motion. And from the video we watched way back a while ago, things like your music that you have, like the music notes, is a change in air pressure where it goes from high pressure to low pressure, and your ear is basically interpreting the changes in air pressure as sound that you hear. And those are also sinusoids for simple notes that are being played. So we're going to look at a couple of examples just to kind of expose you to the flavor of how sinusoids work. All right, so we're going to look at Ferris wheel. I'm going to highlight a couple of important things in the problem. It's a 3-minute ride, so that's kind of important. We're going to a max height, so max of 105 feet and a low of 5 feet. And it's going to rotate at 6 revolutions per minute. And then we're starting at the low point when we do this. All right, so these are all things that are kind of important in terms of determining what's going on in the problem. So the first thing that we're going to do is we're going to talk about the frequency. How frequent does it go around? Well, that's this part right here where they have given us that it's 6 revolutions per minute. Now, kind of looking ahead for that, you could also kind of think of that in seconds. Notice that over here, I'm going to be asking you for angular velocity in radians per second. And again, looking down here in part A, that we want to measure time in seconds. So you do kind of look for key ideas about what units we want. So even though my frequency is given to me as 6 revolutions per minute, I am probably going to convert that to seconds. And so remember that there are 60 seconds in 1 minute. So this is going to end up being 1 revolution every 10 seconds. So that's going to kind of be our target of 1 completion of a cycle that's there. And remember that the relationship between frequency and period is that your period is the reciprocal of the frequency. So once I get my frequency in the correct units, I can just simply flip it and be like, the period is 10 seconds for each cycle. And you'll notice that cycle or revolution, they're kind of the same thing. 1 cycle around the circle, 1 cycle of the graph where you repeat. So it's going to give us a period of 10 seconds. Right? Now, the angular velocity in radians per second, if you will remember, the angular velocity, and I'm kind of putting formulas that I'm using in red, remember that your b in your transformed equation is, in an application problem, your angular velocity in radians per time, where the time is going to match what your x-axis is going to be in. So going ahead and calculating our angular velocity is something that's going to be kind of important for this. So for this problem, right now, I'll just come over here on the side. We have 1 revolution every 10 seconds. And then to convert that into radians per second, then what you're going to do is go 1 revolution is 2 pi radians. And that would give us pi over 5 radians per second. So we're going to fill this in, pi over 5 radians per second. And then we're also going to remember kind of why this works. Like the other way The alternative way of calculating this B value that's going to go into our equation is going to be that, remember that B, I'll write it down here, is 2 pi divided by the period. And so I could go by that kind of target as well, and I can take the period that I have listed over here that I already calculated and put that in for the P right there and get 2 pi over 10, which is pi over 5. But again, I wanted to stress that that B value, which is telling you in several different things, it's the number of cycles that happen every 2 pi. It's also telling us what the angular velocity is in radians per time. So I just wanted to make that connection again. All right, coming back in and filling in the given information. Our max height was 105 feet. Our min was 5 feet. We want to find our midline, and remember the midline is the center of the max and the min, so it's the average. So I'm going to take my 105 plus 5, and I'm going to divide that by 2, and that's going to give me my midline of y equals 55. And then my amplitude is going to be the difference between the max and the amplitude to find that height. So I'm going to do the 105 minus 55, and that's going to give me an amplitude of 50. So all of that is information that you guys get just from reading the problem. Okay, now we're going to go toward sketching the graph of the rider, height as a function of time. All right, so the first thing I'm going to do is I'm going to put my axes on here, and I'm going to kind of, as I'm sketching these in, going to go pretty low here, because remember, our max and our min that we have is 5 up to 105. And I also like to put the midline in, which is in the middle, so I'll kind of add that in. I like to label height as a function of time up here. And I also like to write my units because I would like to pay attention to that. Now our x-axis, as we're going, remember this is going to be our time in seconds, according to what we have up here in the problem. And really what this is we are going to put increments that have to do with our period. And so our period is every 10 seconds. So certainly we're going to put 10 seconds, we're going to put 20 seconds, maybe we'll do 30 seconds, to kind of level that out. Now, if we were to talk about domain, and really what we're going to talk about here is relevant domain, what makes sense in this problem? Our sinusoids in general have a domain of negative infinity to infinity. But for this problem, we're just riding the Ferris wheel, and it's a 3-minute ride. So that's going to tell us that once we start the ride, we're only going to go up to 3 minutes. But because time is in seconds, I do need to make sure that I write it down in seconds. We really want to go up to 180 seconds in terms of our relevant domain for our ride. Now, I'm not going to go ahead and graph this all the way out to 180 seconds because this repeats. As long as I get a couple of repeats of the pattern in, then we're going to be fine and we'll know that it keeps repeating beyond that. All right, the next thing I'm going to do is I'm going to divide out my periods into their 5 key points. Remember, I'll do it for the first one, that halfway, and then divide it in half, 2.5, divide that in half, 7.5. So that when we go to sketch this and we follow our pattern, we know that we're going to oscillate around this midline. And these are going to be the 5 key points where we are going to follow the pattern of the graph. Now, in ours, pay attention to where we're starting. Let's see, where did it say we were starting? We were starting at a low point. So when I start plotting my graph here, I'm going to put this in green, we would start at the low point, hit the midline at the critical key point, 2.5 seconds. At 5 seconds, we had been a max. Then back to the midline, and then add a min. And then from there, we could basically just repeat that pattern, divide each of these into the 5 key points, and you can get the values if you need them. We'll fill them in after. Let's just kind of continue our pattern. Inflection, max, inflection, min, inflection, max, inflection, min. and we'll kind of sketch in our curve here as we go. So this is why, even though the relevant domain is 0 out to 180 seconds, you don't need to graph it for that far, because we know that it's basically just going to repeat this pattern every 10 seconds, which is what its period is. All right, now we want to come up with an equation for this. And so the idea here is that to figure out a particular equation, we're going to identify things like, first we need to figure out a phase shift. We need to figure out what parent we want to use. And those are things that vary. If you remember from our discussion in the last set of notes, that you can choose whether you want to have a sine or a cosine. You can choose whether you want to do a flip or no flip by picking a certain phase shift. So I'm going to start, I'm going to do it a couple different ways. So I'm going to leave these blank, and then you guys can fill in what you choose to go. I'll fill it in for my first one, and then you guys can pick whichever one you want to do. I'm going to decide that I want my parent graph to be a sine function. And if I don't want it to have a flip, let's say I want no flip in there, that means my pattern has to start in inflection, max, inflection, min, inflection. So I have to pick a phase shift that starts at an inflection and is going up as its first thing. So I'm going to go ahead and choose this point right here to be the beginning of my period, because I'm at an inflection and I'm going up from that point. So my phase shift is going to be 2.5, positive 2.5, 2.5 to the right. So when I go down to write my equation, I'm going to go, what's my amplitude? The A is going to be 50. I do not have a flip, so it is not negative as I look at it. Then we're going to put our sine graph in, and we're going to get the B value. Now, I already did the work up here for the B value that I was looking for. So over here, our B was pi over 5. So that's probably why we do a lot of the pre-work that we have. So we put in our pi over 5. Our variable is t, right, because h of t, minus my phase shift is 2.5. And then my midline was 55. And so that would be an equation that I can use. But notice, like, we'll do some alternates here. What if I decided not to use a sine function? Let's change color into green here. So what if I decide to do a cosine function? And I decide to go ahead and let it be flipped, because I notice that here at the very beginning, it just starts at a min. So a flipped cosine would be min, inflection, max, inflection, min. Right? So my phase shift for that would actually be 0 if I decide to start at that point without putting it in. So when I write my equation for that one, h of t would be negative 50 cosine pi over 5. You don't need the parentheses because it's basically going to be t minus 0 and then plus 55. All right, so let's pause here and let's go to the calculator. All right, so as you can see, I have entered both of my equations that I kind of set up in my calculator, but I did want to talk about the window. You cannot just hit graph for these. You are going to have to set the window thinking about the problem. So our x, I usually do something like -5 just so I can see the axis, but really, remember, the relevant domain was 0 to 180. Now I'm verifying, I only want to see what I basically graphed in my hand-drawn graph, and we only really went up to, let's go up to 40. That would show 4 periods. If I don't want to do 4, maybe I just want to do the 3, maybe I'll do that as 30. Now my key points were 2.5 apart, so I'm going to put that in. And then -10 is fine for that, but we have to go up to like 110 to capture our max. And maybe let's go by 20 here just to have a tick mark. All right, take a look at the graph and verify that the graph, oh, that does not look right. What am I doing wrong? My mode has to be in radians for me to be able to do this problem. And I'll talk about why in the next video for that. But we should see that as we trace, we should have the points that make sense to us at 5, we should have 105, and so on. All right, I'm going to stop this video here, and then I'm going to come back and talk about units.